The Fréchet distance is a metric for similarity between geometric shapes. It has a wide range of applications in computer vision, map construction, biochemistry, and more. The Fréchet distance is defined as the minimum bottleneck cost over all possible bijections. An intuitive explanation of the Fréchet distance goes like this. Imagine a man walking his dog on a leash. The man walks on one curve, while the dog follows the other curve. Both man and dog must move forward. The length of the leash is an indicator of similarity between the curves. The decision problem asks, is it possible to walk the curves with a leash of given length? The optimization problem asks for the shortest possible leash, which is the actual value of the Fréchet distance. Alt and Godau presented an algorithm for computing the Fréchet distance for polygonal curves. The key concept of this algorithm is the free space diagram. One curve is mapped to the x-axis of the diagram, the second curve is mapped to the y-axis, spanning a two-dimensional grid or configuration space. Each point in the diagram corresponds to a pair of points on the curves P and Q. The shaded area represents all pairs whose distance is smaller than the given leash length epsilon. We call it the free space area. Watch the free space area grow as we increase the value of epsilon. Next, we are looking for a bijective mapping that stays within the bounds of the free space area. Such a mapping corresponds to a monotone path within the free space area covering both axes. It starts at the lower left corner of the diagram and it ends at the upper right corner. We call such a monotone path a feasible path. How can we find a feasible path? It is not necessary to know the precise shape of the free space area. It is sufficient to examine the transition from one cell to another. The dashed lines indicate reachable intervals. That means all intervals that can be reached from the lower left corner of the free space area. A feasible path answers the decision problem. If there is a feasible path, the Fréchet distance is lower or equal to epsilon. To compute the actual value of the Fréchet distance, we must find the minimum epsilon that allows for a feasible path. An important observation is that the overall structure of the free space area changes only at certain key values of epsilon. We call these critical values. First, we compute a list of all critical values. Then we perform a binary search on the sorted list. For each step in the binary search, we apply the decision algorithm. At the end, we find the smallest possible epsilon that allows for a feasible path. And this is the desired value of the Fréchet distance. For closed curves, the left and right edges of the free space diagram coincide. Just imagine the diagram to wrap around, creating a cylinder. Now the decision problem becomes a bit harder, because the starting point of a feasible path may be located anywhere on the x-axis. Alt and Godau's algorithm is able to find a solution in polynomial time. The Fréchet distance can be easily extended to shapes of 2 or more dimensions. However, computation becomes much harder. Fortunately, the problem is tractable for some surfaces. In 2006, Buchin and Wenk presented a polynomial time algorithm for simple polygons. That is, polygons without holes and without self-intersections. The crucial observation is that the problem can be broken down to certain diagonals of the polygons. The diagonals in P are mapped to shortest paths in Q, with additional constraints applying to those mappings. A large part of the algorithm is concerned with finding valid mappings between diagonals and shortest paths. The following example demonstrates that the Fréchet distance for polygons is actually different from the Fréchet distance of their boundary curves. Using Fréchet View. Fréchet View expects 2 polygon curves as input data. Just store the files in SVG or IP files. There are numerous programs for editing vector graphics files. Save the file and open it with Fréchet View. Use the control panel on the left to select an algorithm. Let's start with the algorithm for polygonal curves. Watch the free space diagram as we modify the value of epsilon. Whenever a feasible path is found, it will be highlighted in the free space diagram. To find the actual value of the Fréchet distance, click the Optimize button. The computation is based on a binary search over all critical values. The Approximate button uses a simpler approach using nested intervals instead of critical values. Next, let's have a look at the algorithm for simple polygons. Separating the display of input curves improves readability. Note the diagonals that play a central role in the algorithm for simple polygons. Click the Decide button to look for a feasible path. Move the mouse pointer over the feasible path to highlight the sections of P and Q that are mapped to each other. Note how diagonals are mapped to shortest paths. Click the Optimize button to find the actual value of the Fréchet distance. Again, Approximate uses a search on nested intervals. You can edit the input curves while the Fréchet View window remains open. Edit your file, then save it. Changes will take effect immediately. A more detailed user guide for Fréchet View is available online. Finally, we present a new variant of the Fréchet distance called the K-Fréchet distance. It was introduced by Buchin and Rifkin last year. The input curves are mapped piecewise, based on a relaxed definition of the Fréchet distance called the weak Fréchet distance. The mapping between the input curves is not required to be monotone, and it allows for a limited number of discontinuities or jumps. Can we find a mapping with at most k pieces? From the perspective of the free space diagram, the task is to select the minimum number of components that cover both curves. The problem was shown to be NP-complete, but also fixed parameter tractable. A greedy algorithm can approximate a solution within a factor of 2. Using our program, we were able to validate this approximation factor. The input curves are repeatedly overlaid, which is somewhat hard to visualize. Note, however, that the resulting free space diagram is composed of a very regular pattern that can be scaled to any size. This example helps to show that the approximation factor approaches the presumed value of 2.